Hello everyone and welcome back. In this video we will look at a couple of things. Here's a summary of what we're going to learn today. First we're going to review what we learned so far, then we're going to learn about stochastic gradient descent, then we're going to learn how we should split our data from the datasets we get, and then finally we're going to look at matrix form to make things much faster. And we're going to code all of this at the end. Alright, let's get started. So the last time, we figured out 8 equations that dictate how we can make predictions with our neural network and how we can train it to make it better. Specifically, these 2 equations dictate how we move information forward. We first take a weighted sum of the inputs, and then we add a bias at the end. And then, by applying the sigmoid function, we squash these outputs between 0 and 1. To update our parameters, we use gradient descent, which is kind of like an algorithm that resembles walking down a hill with fog all around you so that you don't know where exactly you're going and where the bottom is. In addition, this eta right here is a hyperparameter, which means that we control how it moves. These weights and these biases are also learned parameters, meaning that the weights and biases are what we're actually trying to change to make them become better. And finally, we use backpropagation to figure out these changes, and specifically compute the gradients. And this intermediary term delta is used to make the math a lot easier. And when we use all these equations, they become very powerful. But many improvements can also enhance their effect and make them even better than they already are. For starters, let's look at our parameter update rule that we have so far. The way we've treated it until now was to simply sum over the changes over all of our training examples x. And last time this worked because we only had 2 samples of data to our very limited problem. However, to actually generalize, you need to give the network a lot of data. With tens of thousands to even millions of different samples, it becomes computationally expensive to go through all of those samples just to get one update to our network. We could probably get a good summary of the updates needed from just a fraction of that many samples. In fact, if we mixed around the samples in our dataset every epoch and then selected the first couple of them, this would be a decent estimate of the gradient. And that's exactly what stochastic gradient is. We sample m training examples and compute the gradient based off of those. Note here that now m becomes another hyperparameter that we have to choose. You might also notice here that in this equation, the magnitude of the gradient depends here on m. If m is larger, then the gradient will have more terms in the summation, and therefore the gradient will be larger. So to help make this a bit more robust, we can tack on a little extra 1 over m on the end to make this more of like an average. Both of these versions of this algorithm are valid. However, the second one is more commonly used, more widely accepted, makes more intuitive sense, and is the one that we will be using. Note here that to be consistent, our vanilla gradient algorithm should also tack on an extra 1 over n term, where n is the amount of total training examples. Now that's SGD in a nutshell. Now we can move on to how we manage our data. So it's great that we have all this data, but how do we use it? You might say that we should just give it all to the algorithm as training data. But if we do that, we wouldn't be able to really test it and see how good it generalizes to new data. So then you might say, just split your data into 2 sets, a training set and a test set. And this idea is better, but it doesn't account for the hyperparameters. You see, there are many different choices of them, and to get the best combination of hyperparameters, we have to see which combination does the best. And the way we're currently measuring this is by seeing which one does the best on our test data. But what that means is that the validity of the test data being used as a representation of how well our network generalizes is no longer present, since we're biased towards network with hyperparameters that just do best on the test set. We're essentially indirectly training the hyperparameters on the test set. And this brings about an important point. Don't touch the test set until the very end to make sure we can accurately see how good our network is. To resolve this issue, we split the data into 3 parts, with the new part being the validation data. We train on the training data, choose hyperparameters based on the validation data, and at the very end, to see how good it is, we test on the test data. and this is what is used most in practice. As for how exactly to split it up, on large data sets, it's typically 60% training data, 20% validation and test data. However, as your data sets get smaller, it can also be 80%, 10%, 10%. The main idea is you want to have enough data to also be able to choose good hyperparameters and to be able to accurately judge how well it's doing. Going under 10% test data is probably not a good idea. Anyway, now we're ready to make things even more efficient with matrix form. Here's the idea. Instead of looping over all the mini batches and computing each sample in the mini batch individually, matrix form allows us to do it all at once. And matrix form is just a way of looking at the math in a different perspective. The idea is to let all the activations and weighted inputs for the mini batch be stored in one matrix, with each column containing a specific sample's activation or weighted input. And the awesome part about this is that the change that this has on the rest of the math is basically nothing. Now, if you don't really know what's going on here, go check the other video out. I explain what these variables stand for and all of that in more detail. But anyway, as I was saying, the impact that this has on the rest of the math is basically nothing. For example, when we multiply this activation matrix by a weight matrix, the resulting matrix preserves the information about each training example. And the only changes that we really have to add to make matrix form work is notice that when we add the bias vector to every single column in the weighted input matrix, we have to broadcast it to every single column, because you can't really add a vector in a matrix. And on top of that, when we find the gradient of the bias, it's going to also be a matrix, but the bias is a vector. So what we need to do is take that gradient matrix and add its column to get the total gradient of the bias. It's a good exercise in understanding to go through and check that the math really does work out. Anyway, that being said, let's review the code. To implement matrix form, basically all the stuff from last time stays the same. So all the code we got is pretty much the same. When adding a vector to a matrix, NumPy, which is the library I'm using for the linear algebra, NumPy, what it does is it automatically broadcasts the vector to the matrix, so we don't have to worry about that kind of addition. But the gradient problem still exists, so we deal with that in this line right here, this line and this line. What's commented is what was there before, and that's pretty much it. Matrix form isn't that hard to implement, and you're going to notice that with all the changes, well, with most of the changes and improvements we make, they're not that hard to implement. But anyway, now we get to the main part, adding stochastic gradient descent. To start, the method will take in the training data, the learning rate, the mini batch size, the number of epochs, which is how many times we're going to iterate over the training set, and an optional validation data by the name of monitor. Here are just some notes about the format of our data, so if you ever want to use this network, just take a look at that. After that, we're going to define some variables that we're going to need to keep track of. What this does is it saves us from recomputing the same thing again and again, and as you're going to see, these two over here are going to help let us monitor what's going on. And now comes the real part, actually using stochastic gradient descent. The first thing we do is iterate over all the epochs, and we start by shuffling the data that we have. Because remember, we started by mixing the data, and then we took the mini batches. After that, we go through all the mini batches, and we update using our update function. And after that, if the optional validation data is provided, we store how good the network is doing after each epoch using this evaluate function to help us monitor the network's progress. On large data sets, this becomes especially important because it takes a really long time to train these neural networks, so knowing when an epoch is done and whether the cost is really decreasing saves a lot of time. And finally, this evaluate function doesn't just come out of nowhere, we actually have to code it. So this is the evaluate function. It's not too bad. We just take a look at the predictions. We first predict, then we find the accuracy and the cost. And that's it. We've written in 113 lines of code a pretty decent neural network. To test our network, we will use a dataset containing images of 100 X's and 100 O's. In case you're wondering where I got the data from, I wrote a program that allowed me to write the 200 characters myself and then save them. Anyway, here's some functions that allowed me to load the data, because I have it stored in a file, and convert it to a desirable form. This code and the code that will follow aren't too important, as they specifically deal with the format of the dataset that I created. Anything that's important I'll note, so don't worry about that. This part over here, this cell, also deals with getting the data in the correct form. The only important thing to note here is the size of the training, validation, and test sets. Here I use an 80%, 10%, 10% split because there isn't as much data. 200 is not really that much. Ideally, I would use something called cross-fold validation, but that's a bit more complicated and a topic for another video. Now that our data set is loaded, you can take a look at an example image. Here we have an image of an X, and you can tell that I'm very good at writing. Yeah, I'm not that good. Yikes. Anyway, now we train the network. Here I use a 2-layer network, and the specifications of our hyperparameters and other things like that can be read off the code. I found these hyperparameters by changing them a bit and then continuously seeing which one did the best on the validation data. Anyways, here I've run it, and now we can visualize our results using this right here. As you can see, the network starts off not really knowing anything, so it randomly guesses, and as you'd expect, it gets about a half of them correct. Remember, 10 is half of 20. And as it starts to train, it starts to get better, and its accuracy improves. And this is the validation data. The cost also steadily decreases, and that's a good thing, because it shows that our gradient descent algorithm is working. Evaluating our final network shows that we have a accuracy of 19 out of 20 and a cost of 0.04 on the test set, which is pretty decent. And these would be the results that we would then show to others or publish in our paper, since this is our final test set. As a bit of an application, here's most of the code I used to generate the data set. Here, I'll just draw another character. Let's say I draw an O. As you can tell, I'm still very good at writing. And you can see that the network predicts an O with pretty good confidence. And that's great. That means it's working and it's pretty decently generalized. Now, this data set is small, and the problem of predicting an O versus an X isn't really the worst problem that could possibly exist. But if you really want, you could still apply this algorithm to a larger data set, and it would still work pretty good. That being said, this network is still the tip of the iceberg. Researchers have figured out a bunch of ways to optimize this algorithm, and most of the ways mostly fall into the categories of either improving the network architecture or updating the update rule itself. And yes, pun intended. Great, that's it for this video. In the next video, we will take a look at a bit of both of the ways of improving and apply the new network that we'll create to a much harder problem, recognizing handwritten digits. If you learned something from this video and are stochastically thinking about helping me out, please like and subscribe. Thanks for watching.